Okay, let's quickly discuss binary search and some maybe more interesting application of binary search than what you had seen before. So I give you an input which is an array of n numbers, which is sorted, and given a question, given a query x, I would like to know whether x appears somewhere in the array. And you can just do a binary search. And it's a recursive procedure. So first we check if the subarray we currently have is empty, then the answer is no. Otherwise, we find the middle element, the element stored in the middle of the array, and if it's equal to the number we are searching for, we return yes. Otherwise, we continue recursively either on the first part of the array or the second part of the array. So that's the algorithm. And the recurrence, if you think about it, well, we are doing a constant amount of work and one recursive call in the end. By the way, this is sometimes called tail recursion, which doesn't matter for our purposes. Tail recursion, you can remove the recursion. Doesn't matter for our purposes, as I mentioned. So we perform one recursive call of half the size and spend a constant amount of work, right? So of course the question is, what's the solution to this recurrence? Well, this recurrence is very easy to solve because you just write it. You repeatedly open it, right? So this is O of 1 plus O of 1 plus Tn over 4. And so on, and you continue in this fashion, right? It's going to be equal to O of I plus Tn 2 over ups. O of 1 plus Tn over 2 to the I. And of course, the observation is that where 2 to the I is larger than n, we stop, right? So we stop when I is equal to O of log n. And as such, a solution to this recurrence is indeed O of log n. Okay, so that's that. Okay. Now here is an interesting application of binary search. Think about a problem where we know how to decide if there is a solution below a certain threshold, and we would like to compute the cheapest solution possible, right? By just using the optimization version. So to remind you, when we spoke about decision and optimization problems earlier on, I mentioned that if you can solve one, you can solve the other. So here's an example how you can do this efficiently using binary search. And the basic idea is very simple, right? You figure out what is the range of the solutions, values of possible solution, right? So there's a lower bound and there is an upper bound. The value of the lower bound and upper bound depends on the problem. If you're speaking about shortest path, then it usually would be immediate from the problem definition what the values are. And now what you do, you can think about the values here as being integers, right? So the answer must be an integer number. And now what we can do, we can just do a binary search, right? We can search the middle value of the array, ask the decision procedure, is there an optimal solution with value smaller than this value here? If so, we continue the search. If there is a solution with this value, it means that there might be a cheaper solution, so we continue recursively searching on the left. If on the other hand, there is no solution with this value, it means that the solution must be on the right, and we do a binary search on the right side. Okay. By the way, sometimes binary search is referred to as lion in the desert. So the reason is because there was a sequence of papers written in mathematical letters in the, I think, late 30s, early 40s of solving the problem of, I give you a desert, how do you find the lion, right? And these articles were a sequence of articles. They were not serious. They were all jokes. But one of the articles suggested the following algorithm for finding the lion in the desert. You build a wall that splits the desert into two. You recursively search on the right side of the desert. If the lion is not there, you're going to search on the left side, right? And that's it. And you can search for it. There is, in fact, books written on all the papers. And people have suggested really ingenious mathematical technique to hunt the lion. They're all, of course, completely ridiculous. Building walls across the desert to hunt a lion is, of course, not very efficient, unless the lion is very large and made out of gold or similar materials. At least they are not suggesting to comb the desert, which, if you saw Spaceball, you would know what I'm referring to. So anyway, sometimes it's called lion in the desert, doing binary search. Okay, back to our example of using of binary search. So think about the search's shortest path in the graph. And we have bound, we have two vertices S and T. There is a bound B. The price of an edge can be at most B. The prices are integers, so the minimum price of an edge is 1, right? So if you think about it, that means that the maximum price of the shortest path is N times B. And assume that you can solve the decision version. And now you would like to solve the optimization version, right? So given an algorithm, we know how to, in fact, let's not go into that. So let's assume that we have a black box that can solve the decision problem. And now you can just do a binary search on the range of possible solutions from 1 to n of b, right? The cheapest solution must be using at least one edge, so it's priced at least 1. And the most expensive solution would use, in fact, n minus 1 edges with price at most b, so it's bounded by nb. So you do a binary search over this range. Binary search requires log 2 of p and b steps. So we'll get an algorithm that calls the decision procedure this number of times. And if the decision procedure, if the decision procedure is reasonably fast, this is a reasonably fast algorithm for solving this problem, right? And it gives you a flavor of why the decision version and the optimization version of a problem are usually equivalent as far as running time, at least up to some small factors. Okay, this is just the example in detail. Okay, that's it.